Hello students, I welcome you in today's session of physics, and in physics we are going to discuss about the electromagnetic waves. You can see here this is your chapter number 14 and today we are going to discuss this chapter. So before going to start, first have a look what is the syllabus. In this syllabus you have to study about the basic idea of the displacement current, first one. After that you have to study about the electromagnetic waves, the characteristics of their transverse nature, qualitative idea. After that, electromagnetic spectrum, radio waves, microwaves, infrared, visible, ultraviolet, X-rays, gamma rays, including elementary facts about their uses. So this is the syllabus and we have to cover out this syllabus in this chapter. So first one we will discuss about, you can see here what is the introduction given here. In the introduction you can see here we know that an electric current produces a magnetic field. You are familiar with this concept very much because in the electromagnetic induction you have read about this. And the two current carrying wire exerts a magnetic force on each other. So further, a magnetic field changing with the time gives rise to an electric field. Is the converse also true? So does an electric field changing with time give rise to a magnetic field? This is the question is asking here and you have to give you the answer. So Maxwell, I hope you know very well Maxwell, the three equations of the Maxwell argue that not only an electric current but also a time varying electric field produces a magnetic field. So while applying the Ampere circuital law which you have studied in the previous chapters, to find out the magnetic field at a point outside the capacitor which is connected to a time varying current, so Maxwell noticed an inconsistency in the Ampere circuital law. So to remove this inconsistency, he suggested that the existence of an additional current called the displacement current. This is the important one. So first we discuss about the basic idea of the displacement current. Here you can see one, this is the topic 2, the basic idea of the displacement current. Now what's the basic idea is given here. A current in a conductor produces a magnetic field. So the qualitative or quantitative relationship between the current and the magnetic field is given by which relation? Which is your Ampere circuital law, and which states that the time integral of the magnetic field vector B around any closed loop equals to mu naught times the net current I threading through the area enclosed by the loop. So mathematically you can see here, you can write this relations like this. The closed integration of vector B dot dl is equals to mu naught of I with respect to the time. Now what is mu naught here? Mu naught is the permeability constant. Clear? Now to find out the magnetic field at a point P which is outside the parallel plate capacitor, which is a part of the circuit through which the time dependent current which is I flows. You can see here in the figure number 1 which is given below, this one. This is your figure, and from this figure you can easily understand what's going on here. So the magnetic field B at a point P outside a parallel plate capacitor C, which is a part of the circuit through which a time dependent current that is I flows. So for this we take a plain circular loop. So you can see here that the direction of the current carrying wire and which is centered symmetrically with the wire. So we have, you can see here, we derive an expression B 2 pi r is equals to mu naught I by T. Clear? Now consider a different surface. This is the surface area or the circumference, you can say here B multiplied by 2 pi r. So now we consider here different surface S2 between the plates of the capacitor having the same boundary as of S1. So in applying the Ampere circuital law for S2, to find that left hand side of the above equation, which is your equation number 2, this one, and this is your equation number 1. So it's not changed, but the right hand side is 0 as the no current passes between the plates of the capacitor. Therefore we can write it this expression equation 2 like this: closed integration of B 2 pi r is equals to 0. This is the third one. So obviously either equation 2 is correct, equation 3 is correct. So according to the equation 3, magnetic field between the plates of the capacitor C is 0. Clear? So here you can see that the Ampere circuital law seems inconsistent in this situation, and this law must be missing something. So the missing term must be such that one gets the same magnetic field at M as at P. From the figure you can see here the magnetic field at M and at P point from this figure. This is your P point and this is your M point. Clear? So no matter which surface is used. I hope you understand. So if you look at the figure number 1 carefully, we find that through the surface S2 between the plates of the capacitor, variable electric field during the charging of the capacitor due to the increase of the charge of the plates, electric field also increases. Fine? Which is passes if the plates of the capacitor have an area A and during the charging of the capacitor Q is the charge on the capacitor plates at an instant, then the instantaneous electric field between the plate, you can write it E is equals to Q by epsilon naught multiplied by its area, this one. Now what happened? It is perpendicular to the surface S2, then the electric flux passing through the surface S2. I hope you are familiar with the electric flux. The number of line passing through an electric field is known as electric flux. So we can write here electric flux like this. Clear? E dot A, and in place of E you can put the value from here. So you can see here 1 by epsilon naught Q by A multiplied by area. So finally it comes out to be Q by epsilon naught. Fine. Now if the charge Q on the capacitor plates changes with time, so there is a current I which is dQ by dt. So that using equation 4, this is the fourth equation, you can write here, this is the differentiation of flux with respect to the time, and we differentiate whole of the equation. So finally we get here, you can see that I by epsilon naught, or you can write it here epsilon naught d phi E by dt is equals to I. This is the missing term in the Ampere circuital law which we had already proved in our previous chapter in the magnetic field. So the magnetic field at the point P outside the plate is same at point M, just inside the figure 2 you can see here, this is the figure number 2. Clear? So the magnetic field at point P outside the plates is same at point M, as you can see in the figure number 2, as it should be. So the current carried by the conductors due to the flow of charge is called the conduction current, which is your IC. You can see here IC is the conduction current. The current given by the equation 5th is due to the changing electric field. Fine? Or you can say the electric displacement is therefore called the displacement current. This is the important term, so kindly pay attention on this over displacement current. Or you can say that the Maxwell displacement current. So figure 2 shows the electric and the magnetic field inside the parallel plate capacitor. This is the figure of the parallel plate capacitor. The magnetic field be at M just inside the plate, the same at point P outside the plate. Clear? So from this we concluded that the source of the magnetic field is not the conduction current due to the flow of charges, but also the time rate of change of an electric field. So the total current I is the sum of the conduction current, which is your IC, and the displacement current. So you can write it here, the displacement current with this expression. This is the expression for the displacement current. ID is your displacement current, is equals to the epsilon naught times of d phi E by dt. So here you can see that the total current across the capacitor comes out to be I is equals to IC plus ID, and in place of ID you can write this value which we already derived, this one. So you can see here the expressions comes out to be this. This means that outside the capacitor we have only conduction current, means IC, and no displacement current, that is ID is equals to 0. So on the other hand, inside the capacitor there is no conduction current, means IC is equals to 0. There is only displacement current, that is ID is equals to I. Clear? Now the total current which is passing through any surface of which the closed loop is the parameters is the sum of the conduction current, that is IC, and the displacement current, which is your ID. So you can see here, from the above relations you can write this formula: close integration B dot di is equals to mu naught IC plus mu naught epsilon naught d. These all the things we had putting the values from the above terms. So this is known as the Ampere circuital law, this one. Clear? Sorry, it's a Ampere Maxwell law, not the Ampere circuital law. Ampere circuital law you have you had already read in the magnetic field. Now we come to the Maxwell equation. This is the most important topic of this chapter, Maxwell equation, electromagnetic wave theory related to the light. So Maxwell formulated 3 basic laws of electricity and magnetism in the form of 4 fundamental equations which are known as the Maxwell equations. These are the most important equations. These equations bear the same relation of electromagnetism that Newton's law of motion do mechanics. So in the absence of any electric or the magnetic material, the four basic laws of electricity and magnetism, that is Gauss law of electricity. So the Gauss law of magnetism, Faraday's law of electromagnetic induction and Ampere-Maxwell circuital law are expressed by Maxwell equations. So what are the laws which are expressed by Maxwell equations? So Gauss law of magnetism, Faraday's law of electromagnetic induction and Ampere-Maxwell circuital law. Clear? We can express these laws by the Maxwell equation. So these equations give complete description of all electromagnetic interactions. Maxwell, on the basis of his equation, predicted the existence of electromagnetic waves. So first we discuss about the Gauss law of electricity. What's the Gauss laws of electricity? State that the Gauss law of electricity states that the electric flux through any closed surface is equal to the 1 upon epsilon naught times the net change enclosed by the surface. Gauss law you have already discussed in the chapter number 2 or 3, which is in the Gauss theorem. So that is the thing written here. Mathematically you can write it the Gauss law. Close integration E dot ds is equals to q by epsilon naught. Clear? So this equation is called the Maxwell first equation. So in this equation, q is the source of electric field. The equation is true for both the stationary and the moving charges. Clear? So this is the equation number 1. Now come to the Gauss law of magnetism. It states that the magnetic flux through an enclosed surface is 0. So we can write this expression close integration vector b dot ds is equals to 0. This equation is called the Maxwell's second equation. It signifies that the free magnetic poles do not exist. So any volume enclosed by a surface will contain equal and opposite magnetic poles. So leading to the net magnetic poles strength is 0. On the other hand, the free electric charge do exist. So this equation also signifies that the magnetic line of forces cannot start from a point or end at a point. This is they are closed curves. Clear? Now come to the third one, the Faraday's law of electromagnetic induction. Please remember these equations because they are very important one and might be asked in your examination. So it states that any induced EMF which is set up in the circuit is equal to the negative rate of change of magnetic flux through the circuit. So mathematically you can write this expression E is equals to minus d phi b by dt. Since the EMF can be defined as the line or integration of the electric field, so the above relation may be expressed like this: close integration E dot di is equals to minus times d phi b by dt. So thus the law states that the line integration of electric field along a closed path is equal to the rate of change of magnetic flux through the surface enclosed by the surface bounded by the closed path. This is called the Maxwell third equation, and it signifies that an electric field is produced by changing magnetic field. This is the third equation. Now come to the fourth one. What's the fourth one? Ampere's Maxwell circuital law. So Ampere's circuital law was extended by Maxwell on consideration of the current continuity. So it is stated that the line integral of the magnetic field along a closed path is equal to its mu naught times the total current, that is the sum of the conduction current and the displacement current, linked with the surface bound by that closed path. So mathematically you can write it like this: close integration vector b dot dl is equals to mu naught times I plus id current. And you know very well in the previous topic we had derived the relation, that is the displacement current is equals to how much? Epsilon naught times of a de by dt. So this equation is called the Maxwell fourth equation. Now it signifies that the conduction current as well as the changing electric field produces a magnetic field. So thus I as well as d phi e by dt are the source of magnetic field. Clear? Now come to the electromagnetic waves, which is the topic of your chapter. You can see here what are the electromagnetic waves, and this is the figure of the electromagnetic waves are moving around. So the waves in which electric and the magnetic fields vary sinusoidally is mutually perpendicular direction and also perpendicular to the direction of the propagation of waves. Such waves which actually propagate in space even without any material medium are called electromagnetic waves. So note this point here, the electromagnetic waves does not require any material medium for their propagation. Fine, and they are the combination of the which electric and the magnetic field as well, both are moving with it sinusoidally. You can see from the figure number 3, this is given here, this figure, and with the help of this figure you easily understand these are the two waves. The first one is E vector showing the electric wave and the V vector showing the magnetic waves, and they both are moving equally, and there is a phase difference between both the waves. So figure 3 shows a graphical representation of an electromagnetic wave in which the electric field vector, vector E, and the magnetic field vector are vibrating along, you can see from the figure, Y and Z directions. Clear? And the wave is propagating along the X direction. So both electric and the magnetic field vary with time and space and have the same frequency. Clear? So Maxwell predicted that the electromagnetic waves would travel in free space with the speed of light. Clear? So he thus concluded that light itself is an electromagnetic wave which is transverse in nature. So understand it, what kind of nature of light wave? It is an electromagnetic wave and it is transverse in nature. So other example of electromagnetic waves are radio waves, microwaves, infrared and ultraviolet rays, or you can say X-rays. Clear? Now this is the relation between magnitude of electric field and magnetic field in free space. This thing we will discuss in our next lecture. Till that, do study. Thank you class. Thank you.